This lecture is about irrigation scheduling, so how you set your timer on your irrigation controller to turn your systems on and off to take care of irrigating your soils and your plants to compensate for the loss of water due to evapotranspiration, which is the combination of the loss of water from transpiration and evaporation. And I'll probably say the same thing over a few times in this lecture, but water is lost from your landscape through evapotranspiration. Water lost through transpiration is water coming out of the inside of the plant through the stomata and the leaves to the atmosphere. That's transpiration. And water lost from everywhere else in your landscape, the surfaces of the plants, the surface of the soil, everywhere else. That's that's evaporation, and together they are ET, or evapotranspiration. And we are replacing that water loss with our irrigation system. And we need to know the application rate, also called the precipitation rate. That means how much water is coming out of your irrigation system is being applied to your landscape. That should be dialed in specifically to replace the water loss through evapotranspiration. How do you know how much water is lost through evapotranspiration? Through weather stations. Here in California, you use the CIMIS system to determine how much water loss is happening through ET at your site for a given month of the year. And how much water is being delivered by your irrigation system can be measured in a catch can test. And 3, how evenly the water is delivered, or the distribution uniformity. How evenly is that water that's being applied through your irrigation system? How evenly is it being spread out? So is there dry spots, wet spots? That's the DU. Let's start with number 1 of irrigation scheduling. How much water is your irrigation system delivering? Again, the precipitation rate equals the amount of water delivered by your irrigation or sprinkler system in an hour as measured in a catch can test. It's usually measured in inches per hour. So catch can test, in this picture, these people are setting out a catch can test. This is part of a catch can test I did in a course I was taking at Cal Poly, and we put out these little plastic cones in a nice grid-like, semi-regular grid-like fashion, turn the irrigation system on that's already existing on that turf for 10 minutes about. You can do different time amounts, but here we did it for 10 minutes. And then we measure the inches or millimeters in each of those cones and get an average of how much water was applied over that whole area in inches. And then we times that by 6, since we had our irrigation system on for only 10 minutes, and we want to get inches per hour. 60 minutes 10 divided by 10 is 6, so, or 6 times 10 is 60 minutes, so we want to convert that to inches per hour, and the average is then determined thus. And then the system is scheduled to be on long enough each month to replace the water loss through evapotranspiration. We find out here how much our system is applying our precipitation rate of our irrigation system first. This is an example of a laminated chart that shows the different valves and irrigation lines in this little area of turf. It's usually placed in the controller box, so the landscaper or the irrigation maintenance person can see which valves are watering which areas of turf. And that can help you when there's a break in the line to determining precipitation rates and knowing if there's a leak, where it is, and what valve it's on. And the catch can test, like I said, I'm going to repeat this a few times, is used to determine irrigation system precipitation rates, whereas the weather data from Lake CIMIS is used to determine the monthly ET rates. So precipitation rate is how much water is going onto your landscape. ET rate is how much water is leaving your landscape. And your irrigation system, your valves, your timer, your controller should be scheduled, the timing set up to apply the same amount of water in a month as is evapotranspiring. All right, how do you determine how much water you need to replace? Number 2. How much water do you need to replace? That's the ET, or evapotranspirative rate, and those rates can be obtained from CIMIS, the California Irrigation Management Information System. Those are a system of weather stations throughout California. For example, the ET rate for Santa Barbara at Station 107, which is quite near Santa Barbara City College campus, the ET rate for Santa Barbara in June for that month is 5.24 inches. So 5.24 inches of water are evapotranspiring. They're leaving that landscape near that station in that month. That's the amount of water you're going to have to put back. But for now, in this slide, we're just talking about how much is leaving. You do have to make an adjustment also for the type of plant. So if you were, let's say, had all gravel, California gold gravel and succulents, a lot less ET, the ET rate would be much lower than if you had lots of big leafed plants and it was lush or a turf or something like that. So there's a crop coefficient. These terms like crop coefficient, it sounds like we're dealing with agriculture. That's because these terms came out of the field of agriculture from farmers. But what it's saying is the ET rate needs to be adjusted for the type of plant that you're growing. So even though ET rate for Santa Barbara in June is 5.24 inches, that's just the standard, and it has to be adjusted for the type of plant. The 5.24 inches is the maximum amount, as if you were growing a field of alfalfa. That's how much water would be lost. But you adjust it for the type of plant, the particular type, and it changes somewhat. So we need to do that as well. One question. The ET rate is for a general area including all plants. So how do you adjust the ET for your specific plant type? Again, that's the crop coefficient. If you're trying to schedule your irrigation system and receive ET rates from the CIMIS system, the rate's not going to be, again, specific to your plant. It's specific to someone growing something like alfalfa, or which is a high water use plant, or like something like a succulent, which is a low water use plant. Okay, so the ET rate for a specific type of plant, a specific species, is called the crop coefficient. And that coefficient is an adjustment made to the ET rate to make it specific for that particular plant. So when you find out the ET rate from the weather station, it's giving you the rate of evaporation of a very high water use plant like alfalfa, or a high evaporation rate as measured by the station by an evaporation pan at that station. Your plants probably will be a lot less, not a lot, but somewhat less of an ET rate than would be a field of alfalfa or just the evaporation pan. So again, succulents would be much lower ET rate than shrubs and just general kind of shrubs and trees, which would be a lower rate than a turf or tropical plants. And that coefficient, crop coefficient, makes that adjustment for us. Crop coefficients adjust that reference ET rate, again, to your specific plants. So an example, a cool season grass uses 80% of the ET rate that you get off of the weather station. A warm season grass uses 60%. Water-wise trees and shrubs, like think Mediterranean, kind of somewhat drought-tolerant trees and shrubs, only use 40%. Natives, even less percent. So water-wise trees and shrubs, and maybe some Mediterranean shrubs, use only 40% of the water that alfalfa uses. So that means the ET rate has to be ratcheted down by that much for it to be accurate, so you can determine how much water your system should apply in your irrigation. So let's carry on our example. The water plant requirement is the ET rate times the crop coefficient. So in order to determine the plant requirement for Bermuda grass, let's say in June, we already said that in June the ET rate for the month of June in Santa Barbara is 5.24 inches are lost through ET around that this area of Santa Barbara City College and the weather station 107. So how is the ET rate for, so let's just say Bermuda grass, which is a warm season grass, meaning it grows in the warm season, and uses only 60% of the water that the ET rate says. So the weather station says 5.24 inches are lost through evapotranspiration in June in Santa Barbara for alfalfa, or a really high water use plant. But you are growing Bermuda grass, and that only takes 60%. So you times 5.24 times the 60% in decimal form, that's 0.6. And your Bermuda grass is actually only losing 3.14 inches in that month. That's important because then you know that's how much your irrigation system needs to apply, 3.14 inches in that whole month. Number 3, irrigation scheduling. How evenly is that water distributed through distribution uniformity? Here are some examples of what distribution uniformity means. It's the sprinkler heads. If they have good head-to-head coverage, so every area of your, let's say, turf or landscape beds is being covered pretty evenly by your sprinklers, then you have a good distribution uniformity. If there's a lot of overlap, and sometimes sprinkler heads are covering one area 3 different ways from 3 different heads, so there's 3 times as much water going to some areas and 0 water going to other areas, that's poor distribution uniformity. The heads are out of alignment or mismatched. They weren't designed to distribute that water or apply it very evenly. Catch can tests are used to determine the DU in addition to determining the precipitation or application rate. Those things mean the same thing, precipitation rate and application rate. So after the catch can test is run, you can see which areas received less irrigation than others. You can do that just by looking at the amount of water. Also do it using a soil probe to see the different depths that the water went in while that irrigation system was on, and you can see which areas are getting more water than others. See in that bottom right picture, there's a distribution problem of the application of the water, because you see cattails growing there in the parkway between the sidewalk and the street, and even water sitting on the sidewalk. There's just way too much water being applied in that one area. So you know your DU is off somewhat. The amount of pressure in your irrigation system can affect the distribution uniformity. If the pressure is not accurate and even, then it will cause your emitters or your sprinkler heads to function improperly. They might not be spraying out as far as they're meant to, and then you get dry spots. So don't mix different head types in one system. Make sure your pressure is accurate, and that will help have good head-to-head coverage and good distribution uniformity. If your DU is lower than 100%, you need to adjust. That means you might have to have your system on a little bit longer if some areas get less water than others in your irrigation system. So in this example, using our last example of a Bermuda grass lawn in June in Santa Barbara, we determined that its plant water requirement is 3.14 inches. It was 5.24, but then we multiplied it by the crop coefficient, and now we know that 3.14 inches need to be are lost in June in Santa Barbara and need to be applied through your system. If the distribution uniformity wasn't very good, only 50% efficiency of coverage, then we need to divide that 3.14 inches by 50%, meaning 3.14 divided by 0.5 is 6.28 inches. So that means that we need to apply 6.28 inches of water in the month of June to have a good coverage of water and application of water in your irrigation system. Again, it means 6.28 inches of water is necessary to provide the entire lawn of Bermuda grass at least the minimum plant water requirement for June. Hopefully that makes sense to you. We had to double the amount that it says the water requirement is when we determine how much water should be, how much water is being lost from Bermuda grass. But because we have to double that to ensure that every little portion of that Bermuda grass lawn is getting the minimum amount of water needed by the Bermuda grass. If you just did 3.14 inches of water, that's all that the Bermuda grass needs and all that it's losing, and your distribution uniformity was really low, only 50%. That means some of the areas of the lawn are not getting hardly any water. So you have to overwater the areas that are where your sprinkler heads are applying water, so it seeps in and soaks in to the whole area. That's the problem with bad distribution uniformity. You have to overwater in some areas to get the water to spread out into all the drier areas. And now let's talk about some basics of scheduling your irrigation system. Okay, so you figured out how much water is being lost from your landscape and how much water you need to apply, but then how do you schedule your irrigation system to apply that amount? Again, we figured the total run time of your irrigation system. It needs to match the irrigation or the plant water requirement. And the plant water requirement was the ET rate times the crop coefficient divided by the distribution uniformity. Remember, we started off with ET rate was 5.24 inches in June for your area. You timesed it by the crop coefficient that was 60% for Bermuda grass, and then you divided it by 0.5, the 50% distribution uniformity. Wasn't very good. The water was not very evenly distributed, so that got you down to that 50%, which is a low distribution uniformity, and that gave us the 6.28. That's the plant water requirement. And you did a catch-can test, and you determined the precipitation rate was 1.8 inches per hour. So that's how much your irrigation system is applying. If you take the 6.28 inches that's needed by the plant in June, and you divide it by 1.8 inches per hour that's being applied by your system, that means that you need to have your irrigation system on for basically 3.5 hours in the month of June in Santa Barbara for that Bermuda grass with that distribution uniformity. So let's convert 3.5 hours to minutes. That's 310 minutes that your system has to be on in the month of June in Santa Barbara. Divide that by 30 days. It's like 7 minutes per day, but no one has their irrigation system on for 7 minutes every single day of the month. You'd have it less than that. Like, look below at the bottom. If your timer is scheduled to run twice per week, so that's 8 times in a month, how many minutes would you enter into your program? How much time would you schedule each of those 2 times per week, the 2 times that your irrigation system goes on? How long should they be on for those times? Well, you take the 210 and divide it by 8. And then the last question, if you want to run it 3 days a week, you take the 210 and divide it by 12, because 3 times a week times 4 weeks is 12 times a month. So that is how you determine how to actually put the scheduling into your controller for how long it should be on to replace the water that was lost through evapotranspiration, and taking into account the crop coefficient and DU. So hopefully that's not too confusing. We can definitely talk about it more, but I did want to alert you to 2 different types of irrigation controllers, or timers, sometimes called clocks. There's a conventional one, the non-smart, that don't have internet connectivity or any kind of weather connectivity, so they're not taking internet data from the weather stations to adjust their the scheduling, and they're also don't have any kind of like a rain sensor or soil moisture sensor or anything. You just set them for the time you want to, and that's when they go on and off. It's not adjusting at all unless you go out there and manually adjust it. Smart controllers do have internet connectivity to real-time weather data and or some types of attachments like a rain sensor or soil moisture sensor that can adjust for the weather and environmental conditions. These conventional non-smart controllers, some of them have multiple programs, meaning you can have one valve set up for one schedule, maybe once a month it goes on, they're native or drought tolerant plants, and then another valve is set up on another schedule, maybe it goes off 3 times a week because it's on a lawn, or in another one has another program that is set up for let's say just shrubs and trees. It goes off once every week. So there are different programs. That's a normal controller has more than one program, and you can schedule different irrigation regimes, scheduling regimes in that sense. A great, more advanced type of controller will have multiple start times, meaning you can have a valve turn on and off more than one time per day. And that's really good for turf, which gets saturated really quickly. But you could turn your, let's say you turn on your lawn at 5 a.m. to 5:10 a.m. So it goes on for just 10 minutes. By that time, it's probably saturated and water starts to run off, so you don't want it to keep going. But you need to get more than 10 minutes of water applied to that turf in one day. So you might have it go off from 5 o'clock to 5:10 a.m. and then wait for 15 minutes for that water to soak in, then go off again at 6 a.m. to 6:10 a.m. So you're getting multiple start times on the same valve. Water budgeting is it's where the person is pointing their finger to, showing you it's an actual setting on that dial, and you can turn that dial to water budget, input the amount of ET rate for that week. You can get that from the weather stations, or you can get it on WaterWise SB, the weekly watering index, and input. You're seeing here in this image, they input 70% for the water budget. And that means you are setting your controller to deliver only 70% of the water, meaning 70% of the time that you have scheduled it for, and then adjust it for maybe cooler or cloudier weather. And then a rain sensor is something you can attach that'll shut the system down when rain has occurred, and go back on after that little diaphragm in the in the rain gauge after it dries out. So a smart irrigation controller will adjust the watering automatically according to the weather. So your system isn't on during rain, for example, or a cool foggy day. It'll ratchet down the amount of time that your irrigation system is on, and can really reduce water use by your controller and your irrigation system. Again, this is showing you the water budget setting that you can utilize through waterwisesb.org. What you're looking at here is the ET rate in red, and then the dashed line is the typical water schedule. People have their irrigation system on a lot longer in the summer, from April through November, the dry months here in southwestern United States, and then they have it on another setting, like a winter setting. They have a summer setting and a winter setting, and it's not nuanced at all with the ET rate. So that blue area is all the extra water that's being applied in the summer that's not needed, and in the winter, and it's just not changed much at all. That's where we can have a lot of savings of time and money and resources. If you go on waterwisesb.org, you'll find this irrigation scheduling tool. It's not a bad place to start to figure out how to schedule your irrigation timer. You can input the type of plant, the soil type, the emitter type, and even the flow rate, and it spits out an irrigation schedule. It tells you how many minutes your system should be on each month and how many times it should be on each time that it's on. Here's an example output from that same scheduling tool on WaterWise SB. It shows you all the different months, the maximum minutes per start time that system is on, the start times per week that's suggested, and the total minutes per week. And you can just see this is for a cool season grass in a sandy soil with a rotor, the pop-up rotors. And you can see like it just increases. You start in January, needs 44 total minutes per week, but it should be on twice, so for 22 minutes. And that goes up to 4 times a week in June, and 5 in July, for a total of 110 minutes. So you can just see how, of course, the water needs of the plant change throughout the seasons. And then on the bottom is the same lawn, a cool season grass like a Kentucky bluegrass or a fescue, and in a clay soil with the same type of irrigation emitters, the rotors. So, and how that changes, what you see, the overall amount of water the plant needs isn't that different, but the way you apply it is. Let's look at the top. In July, that system should be on for 5 times, start times, each 22 minutes for 110 minutes in a sandy soil, because the water infiltrates quickly. So you can have it on longer. But in a clay soil, the water does not infiltrate quickly. It saturates quickly, so the maximum length of each start time should be only 12 minutes and on for 9 times for about the same amount of overall water. This is another output from that scheduling tool, just comparing it to landscape bed on the top and native trees and shrubs on the bottom. Let's look at the bottom. And July, look at only 27 minutes per week should that system be on. Well, remember, with the turf, it was 110 minutes. So big differences between the type of plant and the evapotranspirative rate, and thus the length of time and amount you should have your system on. Another lawn scheduling tool is found on the UC IPM website, and it's similar to the WaterWise one. You go through the location and other factors, and it tells you how long to have your irrigation system on. You tell them where you're growing your plant. In the last slide here, what you're growing, the type of turf. Here you are inputting your sprinkler output. That could be determined by a catch can test. So after you do all this and dial in your system to replace the amount of water lost through ET, you can create this perfect irrigation system. But even if you do, there's a leak or a break in your system, then you're gonna, all of that efficiency will be lost. So in addition to scheduling your irrigation system correctly, you need to pretty consistently be checking for leaks, pressure changes, which indicates a leak, or wet spots, or rooster tailing, where you have a big spray coming out because a head's popped off. These irrigation systems are really useful, but that doesn't mean they need no maintenance once you got them set up. You've always got to keep checking them in person as much as you can. And there you go.